Welcome to my presentation today, which will take the form of a research and policy-based discussion regarding cross-curricular approaches and discrete approaches to maths and science in the primary classroom. We'll take in the benefits and the constraints of these two approaches and talk about some of the organisational concerns regarding cross-curricular approaches. I think the first thing that is important to understand is that life itself could be said to be cross-curricular. That our knowledge and our understanding isn't separated by the banal distinctions that we encounter so regularly in the education milieu. In layman's terms, our brain is two-sided. Logic does not dispel creativity or vice versa. In fact, the greatest minds often employ both logic and creativity and do not focus rigidly on one subject. Thinkers such as Galileo, Plato, Einstein and Da Vinci are famed for their creative, integrated approach to mathematics, science, and the world. Great feats of engineering have been achieved when maths and science have not been treated as disparate subjects. Maths and science rely heavily on one another as means of definition and contextualization. Max Tegmark of MIT has famously written that the universe is mathematics, that matter is built on number. This is of course only a theory, but the fact remains that science and maths are interdependent. A more holistic approach to curriculum planning seems relevant then, as to teach subjects in isolation could be said to deny the true nature of knowledge, the brain, and of learning. The ideas presented here can apply across the curriculum, but with regard specifically to maths and science, a more creative and dynamic approach is recommended, as we know that maths is most successfully learned when it is coupled with creativity. Indeed, a rigidly segregated approach to maths and science can prove problematic, as abstract concepts such as number require context, provided ideally by scientific inquiry. It may well be argued that science provides real-world context where teachers often rely on tenuous applications. Teaching resources such as Teachers TV are occasionally guilty of perpetuating this problem. Unfortunately, in our current curriculum, such applications are not encouraged, as only one mention is made of linking to maths in the science programs of study. Detractors from cross-curricular teaching cite a number of concerns, highlighting the potential for tenuous interdisciplinary planning and watered-down learning. Such concerns appear to relate more to the teachers of integrated curriculum, though, rather than the notion of integration itself, as little evidence is provided to support discrete curricula. There are, of course, areas of the mathematics and science curriculum which lend themselves less easily to interdisciplinary approaches. Areas such as early number in maths or plant life cycles and living things in science provide very little by way of interdisciplinary linkage. This is healthy, and it is not necessary that every topic area should be linked together. Looking more closely at the areas of study within the maths national curriculum, there appear to be three areas which provide difficulty in applying to science. The majority, however, appear to have close ties to scientific principles. As stated, that some areas do not apply readily is not a cause to disregard interdisciplinary pedagogy. The greatest strength, though, of cross-curricular approaches is the idea of application, that knowledge and understanding may be applied to a specific context. Practically speaking, there are a number of ways that cross-curricular teaching may be planned and delivered. These are discussed by Barnes and by Hurley, among others. The nature of the integration relies heavily upon the pedagogical aim. A number of the options are multidisciplinary and interdisciplinary approaches. However, one of the problems that cross-curricular pedagogy appears to have encountered in recent years is the problem of definition. Various teachers and practitioners have different definitions of cross-curricular approaches. No matter the definition we use, the most important aspect in planning any curriculum, and indeed an interdisciplinary curriculum, is the learning achieved. In an ideal setting, assessment for learning is dynamic, and teachers understand which skills need to be learned by pupils. The skills are more vital than the content, and provide a possible starting point in planning. Unfortunately, practitioners often focus on the content first and ask questions of the skills required later, as a box-ticking exercise on an AP chart. This is where tenuous links are made between topic areas. The diagram is typical of topic-based so-called cross-curricular approaches, where subjects are the starting point. Jagger suffers from this problem also, drawing weak links between Tudor exploration outside Europe and maths through timelines and science through a study of scurvy in humans. While the plan is a step in the right direction, with the central question forming the basis of the topic, surely a better route would be to define the skills desired, to progress learners, and to find content which answers this need. In this regard, skills-based curriculum planning is vital as it provides a stimulus for learners and a blueprint for practitioners. However, it may be argued that this requires a rethinking of existing policy and practice. In mathematical and scientific problem solving and investigation, this skills-based partnership model of planning is yet more essential, as the field shares so much by way of skills and knowledge. Zemelman, Daniels, and Hyde, among others, have highlighted the interconnectedness of the content and pedagogy of the two areas, suggesting that we may improve process skills and higher order thinking by treating them more closely. In terms of differentiation, this seems to present a problem, as various areas of expertise are brought together. What to do, for example, with a child who struggles with place value but is gifted in scientific inquiry. This, however, presents an opportunity to create interdisciplinary mixed ability teams, as Jones terms them, where skills and knowledge are shared. This also goes for teachers, who must plan collaboratively and assess dynamically for the skills needs of the pupils involved. The appropriate use of ICT can aid significantly in the planning and delivery of an integrated science and maths curriculum. ICT may be employed as a means to reduce the burden of planning, as well as analysing and presenting data. There exists a need to teach the link between maths, science and technology as discussed by Berlin and White, and the use of ICT provides this opportunity. ICT also provides the opportunity to escape endless and needless written calculations in maths, and recording and presenting data in both science and mathematics. Using ICT gives more time to focus on mental processes and critical thinking, an idea with which Hiscock agrees. Again, the new national curriculum appears to counter this ideal, virtually forbidding the use of calculators, etc. The thinking seems to be that understanding written calculation affects mental calculation. However, it is the present assertion that in the modern world, focus on high-order mental strategies coupled with the effective use of technology is the means of success, and that dated strategies in maths and science are increasingly redundant. Ultimately and fundamentally, it is upon skills which the curriculum should be based. When focused upon key skills such as analysis, critical thinking, flexibility, and more specific abilities such as problem solving with numbers and interpreting findings, integration and understanding of content is more accessible. Surely it is more important for a child to learn to think critically than it is to know chunking method. Innovative thinking comes through more freedom in the curriculum, rather than rigid structures. Unfortunately, in recent years there have been moves to further segregate maths and science in the primary curriculum. These include the removal of the Year 6 SAT in science, as well as the national numeracy and literacy strategies. It stands to reason that subjects which are tested will receive an elevated status in the primary classroom. Such reforms present a danger to primary science and indeed the entire curriculum, as non-core subjects become more segregated, marginalised and subordinate to maths and English. The strategies have placed almost sole focus on the numeracy and literacy skills required to pass tests, reducing teaching time in other areas. This can be detrimental to the overall learning experience of primary-aged children. Indeed, the research supports the assertion that the numeracy and literacy strategies, coupled with the removal of the science SAT, have demoted science in the primary classroom, further distinguishing between maths and science rather than integrating them. Although the hope was that the dropping of the SAT would reduce teaching to the test and increase creativity in science, the opposite appears true in primary schools. It is argued that this is partly due to the current and recent curricula, which are content rather than skills-based, rigid in nature, and inhibit flexibility and indeed the benefits of cross-curricular approaches. In conclusion, it is vital that children learn the skills to apply scientific and mathematical knowledge to real-world contexts. Anything being taught that does not have an application in the real world has no place on our curriculum. Just as our world is not easily separated and categorized by subjects, neither should our education be. A skills-based, integrated approach to curriculum planning is required to provide children with the tools to succeed. This process is best achieved in the modern classroom when tied in with ICT resources. There should be nothing in the way to inhibit learners' progress. The discussed approach is not without difficulty and is a time-consuming process requiring a paradigm shift in our understanding of curriculum planning and indeed in our practice. Of course, more research is required to ensure that suitable pedagogical and organisational decisions are made. However, any discrete and segregated approach to mathematics and science has the potential to cause significant problems in children's learning. Thank you very much for listening.